All right, so welcome everyone to this tutorial session, the first part of the tutorial session that we are going to see today. And well, after more theoretical introduction of several relevant features for turbomachinery application, we are going to see some more practical example on how to set up a turbomachinery calculation in SU2. Of course, we'll see an easy one. So before really starting to see how to set it up, maybe just a couple of words about why we have this tutorial session in this day. And well, during the conference, I think it was mentioned quite a few times the steep learning curve of SU2, and also we've seen a couple of very nice presentations about developing a user interface, a graphical user interface, which among other purposes was also meant to make it easier for beginners. And I think this tutorial really goes on the same way, and it's meant to help beginners to climb up the very steep SU2 learning curve, which could discourage new users. And of course, also to provide a reference test case of an axial turbine, which is, in other words, this also means that many of these things will be very basic. I know that there are quite expert users in the audience here like in the room. I don't know about people online. So hope it is not going to be too basics for many of you. So what are we going to learn today during this session? Well, we'll see how to set up a steady state runs turbo calculations, focusing on some relevant features of turbomachinery cases. And of course, we'll see how to run a calculation and how to make some turbomachinery post-processing. Of course, our time here is limited, so we'll need to assume some prerequisites. And particularly, we will consider that everyone is already familiar with the basic CFD concepts, such as CFL number, numerics, scheme, in the sense that we won't go into the details. I'm pretty sure that like the audience here knows pretty much more than me, so it should be fine. I'm just saying that you know, for the records and for the audience online. And of course, we'll need very basic knowledge about the usage of Linux terminal or Unix system in general, but just running how to run in a program should be enough. And also, if you want to follow along with your laptop, we will be using SU2 version 8, but not develop or master branch, but these new turbo outputs. You have the link down here, where basically you also have working turbomachinery output in terms of turbomachinery performance and these kind of things. Also, for the post-processing part, we'll be using TechPlot. Of course, I mean, we know it's not a free software. Some institution provides it, some others don't. So if you don't have it, don't worry. In the second part of the tutorial, we'll be using ParaView. So I think we should provide quite a comprehensive overview of post-processing tricks, basic post-processing. All right. So of course, we need a test case. Test case we will be using today is this guy here that I'll be referring to as Aachen turbine, just after the place where it was designed. It's a research turbine. It's 1 stage and a half, meaning that it has one stator, one rotor, and another stator that is exactly the same as the first one. The experimental turbine features 36 vanes for the stator and 41 for the rotor, but here, just to make things a little bit easier and to be able to reuse this setup also for other kind of calculations, such as frozen rotors and steady calculation. Now we basically tuned a bit the blade count such that they all have the same blade count. So it's going to be 41 blades for all rows. Maybe in a while we'll tell a couple of words more about even pitches and these kind of things. The rotor spins at 3500 RPM. The expansion ratio is quite mild, I would say. Overall is 1.4, and it handles a mass flow rate about 7 kilograms per second. So the reason why we chose it is because there's quite a lot of data available in published literature concerning this turbine, and down here you have a couple of references to papers like presenting experimental results for this turbine here. And of course, if you want to follow along on your laptop, you can download the test case here. Like these are just two versions of the same thing. Yes. Which test case repo you mean? The official one? No, it's not yet. No, it's not yet. We'll make it available as soon as possible. In the meantime, you can download it here. Just either click on the link here or just scan the QR code. It's gonna lead to a folder where you have the mesh file, the configuration file, like the master configuration file, and the subconfig for the two stators and the rotor. Also, there is going to be a folder where we have the solution file, the first order solution. Sorry, I hope it was easier. And also there's an equation file that can be used for TechPlot, and we'll be using it for the post processing. So well, maybe let's wait a couple of seconds more in case there's anyone else who wants to scan it.
Yeah.
Okay. Okay. So a very important concept in a turbomachinery application is the periodicity of the geometrical test case, and indeed, exploiting the geometrical periodicity of the system, we can reduce the very complex test case that we were looking at this one, which is way smaller, in which we have just one passage per row. We will have just stator passage, rotor passage, and another stator passage. And well, the reason why I'm stressing this that much is because this is really a wonderful feature if you want to run calculation, because it allows you to reduce the computational cost basically by the number of blade counts, which means you can either increase the resolution of your mesh or just reduce the computational cost, and it's great. So during the previous session, there was a question concerning the pitches, if it's possible to run calculations with different pitches between stator and rotors, or anyway consecutive blade rows. And the question depends on which kind of analysis you want to perform. So well, maybe before going deeper, just terminology. We call pitch basically the distance between the two periodics. So in this case, since all rows share the same number of blades, they all have the same pitch. So it's I mean, of course, it's not a very realistic case, because in reality, turbomachinery never features the same blade count. Otherwise, they just go in resonance. But in this case, I mean, you don't need to pay attention to it. If you're running a calculation for a case that has different blade count for stator and rotor, if you're using a mixing plane interface between stator and rotor, it doesn't matter. You can, well, because just the pitch is stretched when the information are passed from one side to the other. Instead, if you're using another kind of interface that was not mentioned or just slightly touched during the previous session, something like the frozen rotor, pitches have to be equal, unless you have some more fancy boundary conditions for the periodics, which we won't talk about during this session, and I think are not even available in SU2. So this being said, during the tutorial, we'll be using this mesh here. It was done with TurboGrid. It's a structured mesh, and it features about 800,000 elements in total. So it's a pretty coarse mesh. It has some boundary layer refinement, as you can maybe see a little bit around blade shape, but it doesn't have tip gap. Also, Y plus is probably not small enough. And just to make this very clear, this mesh is not for experimental validation. During the post-processing, we will see how you can do something for the experimental validation, but if you want really to validate your CFD calculation, this mesh is not enough. You will need to like experiment a bit and make it more refined. Yes. Oh yes, sorry. Thanks for pointing out. So for the online audience here in the room, it was asked what is the word, like what does the word tip gap refers to. So generally speaking, turbo machinery have a gap between the end of the rotor blade and the upper surface, the casing of the machine, which is needed, of course, to prevent disasters to occur, because we need to always make sure that the blade doesn't touch the casing. So there are cases where you have some sort of additional surface enclosing all blade passages, but still above that you would have some clearance to guarantee that you know, the machine runs safely and it doesn't touch the casing. So of course it's very important because it affects quite a lot the solution, how the flow fields develop within the blade passage, and usually it just determine the appearance of a leakage flow, which then rolls up into a vortex and can take some space in the blade passage. However, here it's not included, it's not modeled. So what's on the agenda? Well, a few things. We'll just say a couple of words about the mesh, just concerning the boundaries. Then we'll have a look at the relevant configuration file section, the one that we care about for our turbo machinery calculations. Then we'll see just very briefly how we can obtain an SU2 mesh. At least one of the ways. I think later on during the second part we'll see other ways. And of course, how to like monitor convergence, how to enforce like convergence criterion, how to run a calculation, and how to make basic post-processing. Let's start with mesh boundaries. So as probably like I think everyone here knows, the SU2 code has its own mesh format that has the SU2 extension. It has a very nice feature that it's human readable, so you can just open it with the text editor and then have a look at it inside. But I mean, there could be way more to say. Just what like matters for us now is that there are these marker tags which allow to identify all the boundaries in the mesh. So there is going to be a section in the mesh file that looks something like this, that starts with this keyword and mark, followed by a number, which basically specifies the number of boundaries that we have in our mesh file. And then we will have as many other sections as the number specified here, starting with this marker tag, which basically is just a way to say these boundaries is called, as it's written here, like hub1, followed by the number of elements which define the boundaries, and all the list of the elements defining the boundaries, and some information about the kind of element that we're using. So why are we like wasting time to say that we have this marker tag? Well, these are important to us because, of course, when we will be applying boundary conditions to all the boundary in the mesh, we'll be using these names of the boundaries just to identify them. So this being said, we can move to the config section. And we'll start with some boundary conditions which are not specific to turbomachinery cases, but maybe more general. The first one is the adiabatic non-slip boundary condition. I mean, I'm pretty sure you're all familiar with that, but maybe it's worth still saying a few words. When we are running a viscous calculation, such as a runs calculation, we have to specify on walls momentum and thermal boundary conditions. And when we specify, I mean, usually we specify this no-slip condition that basically force the fluid velocity at wall to be 0. And then we have to say something more about what's going on from the thermal point of view. And it's very common to perform turbomachinery calculation assuming that the component is adiabatic, in the sense that, meaning that it doesn't exchange heat. So in a turbomachinery calculation, we will be using these boundary conditions for the surfaces which are highlighted here in gray. So the hub, there are these surfaces at the lowest radius, the blades, which are, I think, very easy to spot here, and the shroud, which is the surface like at largest radius. So to apply this boundary condition, we can use the marker heat flux, specifying a 0 value for the heat flux. So the syntax will look something like this. So marker tag, referring to the boundary that which we are applying this adiabatic no-slip condition, followed by the heat flux value that is 0. So for the first component, this is going to be, as an example, blade 1, heat flux 0, hub 1, heat flux 0, shroud 1, heat flux 0, and so on for all the other components, like all the other rows. Another very important boundary condition that is also not like specific to turbomachinery application is the periodic boundary. That well, in the introduction, I've said that we can exploit the geometrical periodicity of the system, reducing it to the flow domain that we see here. But when we do so, we need to make sure that whatever happens on a side of the domain on this purple surface is consistent with what happens at the other side. And this is enforced by a periodic boundary conditions, which, for instance, guarantee that if there's a mass flux going out of this surface, there is going to be a mass flux getting in the other side. So we will specify this with this marker periodic, where we have just the name of the two periodics, the rotation centers about which we make the rotation, the amount of rotation between the two boundaries, and eventually some translation component, which of course is not considered in this case. So as an example, this would be for the first stator, we would have the marker of the first periodic, the one in purple, followed by the same periodic, and then some numbers, which literally means that the brown periodic can be obtained rotating the first one by this amount here, or rotating it around the z-axis, because this is the z component of the rotation, about an axis that passes through this point of coordinates 0, 0, 0, that is the origin. If we were running a calculation for a linear cascade, then we wouldn't have a rotation, but instead we would have translation here, in the sense that one periodic could be obtained just shifting the other one in the direction. Okay, now we can jump to something maybe a bit more interesting that is specific to turbomachinery application, and it was mentioned during the introduction. That is the non-reflective boundary condition. So, of course, as we understood during the introduction, we have to make sure that on our inlet and outlet domain, inlet and outlet boundaries, we don't have spurious wave reflections, which would affect our solution. We do this via the marker Giles, that is called after like the guy who pioneered this concept. And we will have one section for the inlet and one for the outlet. which will look something like this: the name of the marker to which we are applying the boundary condition, followed by the real boundary condition that we are specifying, and then the specific values. It's very like the usual way to run turbo machinery calculation is to specify the boundary conditions in terms of total quantities for the inlet, so pressure, total pressure and total temperature, and also the flow direction specified in terms of normal to the boundary, tangential to the boundary, and span-wise direction, that is from hub to shroud. Whereas for the outlet boundary, we usually specify the static pressure. But as it was pointed out during the previous part, we have several ways to specify the static pressure boundary condition. Why is that? Well, the reason is that we can either specify a constant value of static pressure that has to be respected at each of the span-wise section, or as it is done here, we can specify the static pressure 1D that is more flexible, or it allows the calculation to have a little bit more freedom. If we specify the static pressure 1D, what happens is that the code will compute some, during the calculation, whenever it has to check if the boundary condition is matched or not, at each span-wise section, the code will compute some average static pressure at that specific span. And then their average has to match the value that is specified here, which is, of course, less constraining than requiring each of those sections to respect the static pressure value. So when do you have to use one or the other? When we run calculations for axial machine, we have something called radial equilibrium, which requires flow element to be in radial equilibrium, meaning that the forces are balanced, radial forces are balanced. Because of this, without going into the details, what happens is that you will have a distribution of quantities from hub to shroud. Therefore, also static pressure will change from hub to shroud. So if you're running a calculation for an axial machine, you have to use, or it's highly advisable to use static pressure 1D. Instead, if the boundary is maybe the outflow of a centrifugal compressor where you don't have the radial equilibrium, then you can use just static pressure. As an example, in this case, we would have the name of the marker, so the inflow of the stator one, total pressure and total temperature, followed by the numeric values, the flow direction, some relaxation coefficient, and then the same for the outflow. So the name of the boundary, static pressure 1D, and then the value, and just some values that are not used, and then relaxation factors again. If you want the calculation to be really like to consider non-reflective boundary conditions, you have to activate this additional option that is spatial Fourier. So if you set it to no, the calculation will be reflective in the sense that boundaries will be reflective. Yes makes them non-reflective, so it's better to use them with yes. And then there are some additional relaxation factor for the hub and shroud that can be used maybe to tweak a bit the solution if there's something that doesn't work for you. But this will be maybe a topic for the next tutorial. So what happens if we also have a mixing plane? We have learned in the previous part that mixing plane can be reflective as well. So in this case, we'll be having a mixing plane here and a mixing plane here at the stator rotor interface, and we need to make sure that they are not reflective as well. Because of this, in the marker giles, we will also have an additional entry referring to the mixing plane, where we have again the name of the marker, followed by a specification that tells us if there is the outflow of a zone or the inflow of the zone. And then again, some voids and under relaxation factors. As an example for the first mixing plane, this will be written in this way. So we'll have the outflow of the stator 1. There is a mixing out because flow is coming out of the stator. Just voids, you can ignore them. And but I mean, you have to leave something written there anyway. Under relaxation factor, and then the inflow rotor, that is the next surface, there is a mixing in because flow is coming in the rotor, and then again just these voids and under relaxation factors. And it's also very important to tell the code that there are some interfaces between zones, and this we specify this just listing the name of the surface which represents the interface between the zones. So in this case, it would be outflow stator 1, inflow rotor. And then also, of course, for all the other interfaces in the calculation. Then we mentioned this shroud. So when we make a steady calculation, as we will see in a moment, we'll have to specify a rotational velocity for the rotor. However, in real life, the shroud surface, that is like the surface at the highest radius, doesn't move, in the sense that it doesn't rotate because it's part of the casing of the machine, which means that this surface here doesn't have to be rotating together with the rest of the domain. And you can specify this via the marker shroud, in which you just list the markers that for which you require this option. So whenever you specify a marker here inside, and that marker is the surface that belongs to a rotating domain such as the rotor, what happens is that the grid velocity at that surface that you specified is set to 0. And as an example here, this I mean we could type it this way, just marker shroud followed by the name of the 3 surfaces, although just the second one belongs to a rotating component. So this grid velocity equal to zero would be applied just for the second one, because the other 2 are not rotating. Then turbo performance, like in the previous talk, we've seen that turbo machinery or turbo machines in general have their own way to compute performance. We have total to static, total to total efficiencies, and in order for them to be computed, we have to specify which are the inlet and outlet surfaces to each of the components which contains a blade. So in this case, we would do this via this marker turbo machinery, where we list all the couples of inflow and outflow to each zones that contains a blade. And as an example, for the first domain, these would be inflow stator 1, outflow stator 1, and of course we should make it for each of the domain. But then, as it was pointed out in the previous talk, we also need to specify the kind of like the layout of the machine. It could be an axial machine, it could be a centrifugal machine, and the code needs to know this information because this changes the way in which basically span-wise and like pitch-wise directions are identified, and also the normals on the surface. So for each of the domains, we'll have to specify the layout, that in this case is axial for all the 3 stages, for all the 3 blade rows. And finally, we also have to specify which kind of turbo machine is that. In this case, we're considering a turbine. So for each of the domain, for each of the zones, there are 3, we will have to specify there is a turbine. And in this way, the code knows like how it has to compute performance, efficiencies, and so on. Yes.
This is a very
It's a very,
I'm using version 7.5.
yeah, it wasn't there. Indeed, indeed. And also,
It's an option in user plus if you don't have it in your simulation one start, I would say the beginning simulation rules are right and that's normal.
Yeah. That's right. And also, if you want to run this test case with develop or any other branch which is not neutral outputs, you have to remove this keyword, basically. Okay, then we have been talking about this rotor that rotates, and we have to specify this. Probably the best way to do this is in the sub configuration file of the zone that rotates, as we will have like a master config file that you will find in the folder to which that link was pointing to, and then inside the master config file you will find sub configs for in this case the stator, the rotor, and the second stator. So in order to make this rotor really spin, we have to include this keyword grid movement rotating frame, and also we have to specify the motion origin, that is basically identify a point through which the axis of rotation passes through, and also the rotation rate, that is basically the rotational velocity of the component. It's specified in radians per second, and we have the X, Y, and Z component. In this case, the rotor is rotating about the Z axis, so we only have the last component, and the sign is determined according to the right-hand side rule, basically. So according to the orientation of the axis. All right, so analysis and post-processing. Of course, we want to be able to post-process our calculation in the best way, and for that we need some particular information. As an example, it's very useful to have, of course, it depends a lot on the case you're running, but it's practical to have information from the flow solver of what's going on the blade surface, because you can use that, as we will see later, to maybe extract the blade loading. There is a quantity that is often available from experimental side, so you can use it to compare numerical and experimental results. And in order to specify all the surfaces for which you want this information to be written, you will include this marker plotting and then the list of the surfaces for which you want these informations. All right. Now that we have set up all our config, we can convert, or we can see a way to convert our CGNS mesh to the SU2 mesh. Or people might be wondering, how do I get the SU2 mesh? Well, an easy way is that after you have like applied boundary conditions to each of the boundaries in the config file, what you can do is just provide an input mesh in CGNS format and require an output mesh in SU2 format. You will just provide these two information here, the input mesh file, the file format, that is CGNS, and the output file that you want, so that is the mesh in SU2 format, and you just run SU2 def followed by the config file, and you will get your SU2 mesh where you specified. Just simple as that. So as we were saying, we want to be able to like monitor our calculation, the convergence, and we want to establish convergence criteria. When we run the calculation, as we will see in a while, we will get some output similar to this. First of all, we will have a summary of the turbomachinery performance, so total to static, total to total efficiency, and a list of residual values. Of course, your values are nonsense. because as you can see here, this was the very first iteration. The interesting thing is that you can customize this output that you get in the terminal in a very simple way. You just add to this keyword that is present in the config file, screen output, the list of the quantities that you want to be written in your terminal. So as an example here, we have residual for density, X momentum, momentum in y direction, and energy, and the number in brackets is referring to the zone. So 0 is the stator, 1 is the rotor, and 2 is the second stator. Convergence criteria. So it's a good practice to, besides setting a maximum number of iterations, setting a convergence criteria. That means that if you reach that, your calculation will stop. As an example, you can specify the density residual, or I mean any residual that you think is meaningful for your solution, followed by a required minimum value. Of course, here it's extremely low. Generally, you don't need to go that low. It could be maybe -7, -8. It really depends on the application. It depends on whether you want to run an adjoint calculation later on, and so on. Okay, now we're ready to run our calculation. This is very simple. You can just type in your terminal session SU2 CFD and followed by the config file, and this will run the calculation. So, and then of course you wait for the calculation to start. And well, if we want to do this, we can just open a terminal. Yes. Top. Oh, upper left. You said where? I'm not sure I'm not sure what you want to. What is it? Oh, okay. Yeah. Thanks. All right. So in this folder, we have our config file, and we also have the sub config file that are here: stator 1, CFG, stator 2, rotor, and so on. So we, if you want to run the calculation in serial, you can just type SU2_CFD, and then the number, the name of the config, CFG, and you just run it, and the calculation starts. And of course, I mean, in a while after it has done all the necessary pre-processing operation, you will start getting the all the required screen output. So if you want, you can start running the calculation on your computer, and if you want to run it in parallel, you just add, before SU2 CFD, you just add MPI run -n, and then the number of processors you want to run. And as you can see now, we have these stage performance information, and then we have all the residuals. All right, back to our presentation. Yes. Yes. If you don't have it, please send that main config goes to parallel. Yes. Or just you need the tactile asset management goes to parallel or parallel multi-block. Yes, parallel multi-block, you also get like yeah. And the other one is about the frequency set 500 iterations. Then case like that. Yeah. So you might want to, just run 10 iterations, one solution kills the solution, and start up with the effect. So you can take a look at the geometry. Just put it on. That's right. Yeah. So thanks for the comment. Yeah, indeed. Now we are going to see a little bit of post-processing. Just before that, how much time do I have left, Matteo? How much time do we have left for? Okay, it's perfect. Okay, so like we can leave our calculation running, or we can stop. In the folder you also have, okay, let's leave it running. Anyway, in the folder that you can download at that link, you will also have a first order solution that we can use for the post processing, so we don't really need to wait for the calculation to write a solution after 500 iterations. So let's run it again so that we leave it running. And okay, so as I was saying, we can move to the last section. That is the post-processing that, as I mentioned before, will be done in tech. So we'll see some basic things, of course, which probably for people here would be very, very basics. Maybe for someone that is not particularly experienced, could be new. So we'll see how to make some averages of non-uniform flow quantities, how to make a multi-passage flow field representation, a blade-to-blade view representation, and some tricks for the experimental validation. All right, so it's quite common in a turbomachinery application to encounter non-uniform flow. And as an example here, you see the surface behind the first stator. Here it was pressure, static pressure, the quantity that was plotted here. And as you can see, this is quite non-uniform, both in span-wise, that is from lower to higher radius, and also in pitch-wise direction, that is along this tangential direction. However, besides like having these nice and colorful plots, usually we base our engineering decision on charts and number. So it's very useful to have the chance to take averages of this non-uniform flow. Well, how can we do these things in TechPlot? We can just integrate the quantity on the surface. And for that, let me open a TechPlot window, which is going to take a bit. And in the meantime, it's on desktop, I think, and is in material workshop, test cases, again. All right. So we go in the solution folder and we load these three files that are basically the solution of all the flow domain and these surfaces here, sorry, which are the surface I was mentioning before for the marker plotting. Okay, and we okay. And we open that with the TechPlot data loader. Maybe for this, we'll use a mouse. So in the meantime that it loads the file, I'll just set up the environment a bit. Right, maybe in the meantime that it loads, we can also start to see the next point, and then we do them all together in TechPlot. So, well, since we reduce our computational domain as much as possible to one passage only, the solution that we will have only contains one passage. However, we might want to see the solution for several blades. That's first of all very important, I think, to read more easily the flow field, and also if you want to make sure that your calculation is really periodic along these periodic lines, I think it's much better to have several domains or several flow passages. How do you make this, and how do you pass from single passage to multiple passage representation? Well, from a conceptual point of view, it's a simple operation. You just have some sort of for loop that loops on the number of passages, and inside that you duplicate the solution, so one passage, and you rotate it by an angular pitch, and you keep doing that for the number of flow passages representation that you need. But in TechPlot, there's recently they introduced a more easy way to do that, which we will see. So first of all, let's disable this bounding box here. Okay, so this is our solution. That for some reason is not shown for the volume. Interesting. Okay, maybe it's easy to load them in two steps. So sorry for the inconvenience. We will just open it again, and we will start loading only the flow domains. It's gonna take a bit of time. Sorry for that. And later on, we load also the surfaces. Okay, let's give the computer a little bit of time for that. Hopefully not too long. All right, maybe it would have been better to load them before starting. Anyway, too late for that. Okay, so here we have our flow domain, and it's one passage, as we were saying. So let's start with the first thing we mentioned. So what if we want to take the average maybe on a surface behind the stator? So let's disable these and activate the slice. Let's say that we want to slice orthogonal to the Z plane. We will just place this surface where we want to have this information, and then we just extract the slice. After we have extracted the slice, we should have a new zone here that is a slice we extracted. So what if we want to have information about this slice? So maybe just to make it easier, just let's visualize the slice, this one. So let's say that we want to know what is the average pressure on this slice. Very easy. We just go on Analyze, Perform Integration. We pick the zone for which we want the integration, so the slice we have just extracted. We select the variable for which we want to compute the average value, and we select the averaging technique. For instance, we can use mass flow weighted average, and we integrate. Okay, for that we also need to specify the field variable. That is basically the momentum quantity in the 3 directions. So for the U, we'll have momentum x. momentum Y and momentum Z, and also say pressure, temperature and pressure, and we select the respective variable here. And now we should be ready to go for this simple operation. So integrate. All right, and we have the result of our integration. So this is the value of the average pressure on the surface. Okay, so now we can delete this zone that we have extracted, since we don't need it anymore, and we can move to, okay, we can move to the next point. That was how to move from this single passage to a multiple passage representation of the solution. But before we do that, let's also load the surfaces. Okay, so just to see them, these are the surfaces that we have just loaded. So, and also for as we have for the volume, for these we will also have temperature, pressure, and all the other variables information in the solution for these surfaces. Okay, so as I was mentioning, if you want to move to a multi-passage representation, either you follow the conceptual step and you write a small script with the for loop, or in newer version of TechPlot, you can make that in a more easy way. You can create a zone with this axial duplication. You specify that we have 45 repetition of this domain in the 360 degree, and we say that we want just maybe 3 repetitions should be enough about the z-axis, and we specify the number of zones which should be duplicated, and there it is. We have the multi-passage representation of our domain. Very easy. And now it gets much easier, like to see, for instance, if the result of our calculation is periodic, or if along the periodic lines we have some discontinuity here. And also it gets way easier to read your result, to understand the flow field, and to see if the results you got are physical and make sense. Okay, so now we can move to the next point of what we can do to post-process our calculation. And well, we can see the blade-to-blade flow field view. And first of all, what is this blade-to-blade flow field view from a conceptual point of view? What we do is basically to make a cut with a cylindrical surface of this domain. And we obtain a cylindrical surface on which we can plot quantities such as maybe Mach number or pressure field, again, to see how it looks like and to understand the flow field. But then in order to visualize it properly, we have to unroll it into a planar surface. And also, if we want to be able to perform numerical calculation, numerical comparison, for instance, with experimental data, we have to be able to extract these slice in order to have it for numerical post-processing. And well, this is okay. Maybe the change in hardware made some tricks here. We should have just one of these anyway. Which are the steps that you need to take in order to make these and to be able to extract these slice? Well, the first thing to consider is that TechPlot allows you to extract and to slice and to extract with planes which are orthogonal to one of the 3 Cartesian axes. The problem is that the Cartesian axes are X, Y, and Z, while we want, and our solution is written in this way, but we want to make the extraction orthogonal to the radius. So what we have to do, first of all, is to compute some additional quantities like radius, angular coordinate, and their product, which would represent the length of the angular length of the cylindrical surface. So just coming back to where we have a nice plot, would be basically the length, this length here, the tangential length. Once we have this information, we can change the axis assignment and moving from these x, y, and z to r theta, and z. Once we have this, we are able to slice the domain at constant r, extract the slice, and plot it in 2D under the form of r theta versus z. And let's see how it practically looks like. So the first thing we have to do is to load some equations which are included in the folder. There it is. And these equations allow us to calculate, as I was saying, the radius, tangential coordinate, and their product, so that we have the angular coordinate, the angular length, and we can then unroll it. Then there are a few additional equations to compute the flow velocity, x, y, and z, the velocity magnitude, speed of sound, and the velocity in the relative frame of reference, and finally velocity magnitude in the relative frame of reference and relative Mach number that we need to see the flow field in the rotor. Yes. At which, so the values of the minimum and maximum radius. Yes. Okay, let's compute first these equations so that we also can have information about the radius. We have computed them all for all zones. So we go to data, dataset info, and we pick the radius. So the minimum radius is 0.249027, whereas the maximum radius is 0.32501. Is that okay? Okay. All right. So if we just want to look at the maybe the flow field still on a cylindrical surface, what we can do is just to make an isosurface specifying that we want it for a constant radius value. Like we have to make a little bit of a pre-operation, so we should set the radius here. Sorry for these. And let's say that we want to see the relative Mach number. And what we can do now is saying that we want an isosurface defined based on the radius for a specific value. Maybe let's do 28, that is close to midspan. Maybe to make it more easily visualized, let's also show the blade surfaces. Okay. So as we can see now, we have a surface that is very close to midspan. Let's say that we want to plot the relative Mach number on this surface. Just go here and pick the relative Mach number that we have chosen from the contour panel here. And this is how the flow field looks like. But of course, it's not really practical to have it on a cylindrical surface. And also here, this way, we cannot extract quantities as, for instance, the blade loading. This is why we have to go another way, and we have to do a little bit of a trick. And we just change the axis assignment. And as I was mentioning, we assign to the first axis the radius, to the y direction we assign the product of r theta, which is basically this length here, this angular, the length of this angular arc, and we leave z. Once we do that, of course, our domain will be rearranged. But now we can slice, and we can slice at constant radius because to the x-axis we have assigned the radius. So if we pick the x-axis, we are basically slicing at constant radius, precisely at this value. Now, what we can do is just extract slice, and we now have this surface on which we will have all the information we need to make this plot planar. And what we can do is basically opening, opening another, making another frame. And let's make it 2D Cartesian. And well, maybe it would be easier to open another window, but let's see if we can do it this way. Otherwise, we open a new one. So just deactivate everything. We leave this one. And we have to assign for the horizontal axis the tangential length, so to say, so the product r theta. And on the vertical axis, we can assign z. And oops, didn't get it, didn't got the right one. Okay. And well, now we can just plot maybe the density or whatever we want. Maybe the relative Mach number. Also, maybe we can do it a little bit easier to visualize, reversing the vertical axis. And here it is. This is the, let's change it, sorry. This is the relative Mach number distribution. Of course, for the stator, for the two stators, it's the same as the absolute Mach number, whereas for the rotor, it's different. And now we have, I mean, it's much easier to visualize the flow field, and we don't have like to worry about the perspective and the direction from where we are looking at the flow field. So what if we also wanted to extract quantities along the blade? So just as an example, it's very common in literature, and also, I mean, in research, to compare experimental data against CFD data, just plotting the blade loading or the pressure distribution or the isentropic Mach number, and to have the comparison of the CFD data that is here shown with this solid line against the experimental data that are shown with these dots. So how we can do this thing in TechPlot maybe? So the first thing is that we have to slice the domain and then extract it again. So exactly as we did before, maybe we can delete this frame. We don't need it anymore, or maybe I don't know. Let's keep it, but let's keep it small. If we go back to the main frame where we have our 3D data, and we go again to the slicing section, instead of slicing through the volume, we can select slice through surface zone, which are basically the intersection between these surface with which we are slicing and the blade surfaces. And we select through surface zone and extract slice. Now, in the dataset info, we have another slice, which this time contains only quantities along the surface because we selected slice through surface zone. So what we can do, just as an example, we can make a new frame. We can say that it's a XY line. Let's call it blade loading. And we can plot maybe the axial direction along the horizontal axis, and for the vertical axis, we could see the static pressure, for instance, that it's typical quantity that could be obtained from an experimental campaign with pressure taps along the blade surface. So we select the last zone, last slice that we extracted, and here it is. So let's make it bigger. These are the pressure distributions for the first stator here. This is the pressure side, and this down here is the suction side. This is the pressure distribution for the rotor, and this is the pressure distribution from the same state, from the second stator, and we can very easily spot that the incidence at the second stator is not very well. Sorry. Oh, sorry, I thought it was a question. We can easily spot that there's something that is not working great with our second stator, because we see that the pressure side and the suction side distribution are intersecting, meaning that this section is not contributing basically to the lift. And this is usually the effect of an incidence or the stagnation point not placed where it should be. And this is something that we can easily see if we look at the original chart that we made. We can easily notice this. If we look close to the stator, we can see that the stagnation point is too much shifted towards the suction side. And because of this, then we have this overlapping or this intersecting region. All right. So this concludes, I think, the tutorial session. So at the end of the presentation, you have some references with to material that you can be interested in. Well, you have the link to the branch that was used for this calculation, some information about the some links to papers in which you can find experimental data about this turbine, and finally some information about how the mesh is structured in SU2. All right, so this is all from me. Thank you very much for listening. Yes.
I guess, like, what do you need to do to fix that?
Well, there are multiple things that you can do. So not talking specifically to this case, but yeah, I mean, what you see here, it basically means that there's a sort of mismatch between what the rotor is delivering, the flow field that the rotor is delivering, and what the following stator is designed for. So if you don't want to touch the rotor because you think that it matches perfectly your mainline design or whatever, what you could do is basically changing as an example, the inlet metal angle of the stator in order to try to compensate for this offset. Or maybe another thing which is more probably more advanced, playing a bit with the stator design, maybe changing the pitch, and the effect usually is that the induced velocity component at the inlet due to the circulation of the vane changes, and because of that you have a different incoming velocity. And playing with the spacing, you can basically play around a little bit with where this stagnation point lays.
I was curious, like, isn't this what having an impact on the stage-to-stage efficiency?
Yeah, very much. Well, what happens is that pretty sure that after this stator, you would have a second, I mean, in real life, you would have another rotor. Otherwise, it wouldn't make sense to have a stator like this with such a high outlet flow velocity. So this is not just an outlet guide vane, it's really a stator. So if the incidence is not optimal, or and the stagnation point is not where it should be according to the vane design, you basically add additional losses because of these incidents, because then the flow field, it has to like go around all the stator up here, and this can easily lead to separations or just like additional losses. So it's better to fix it, I would say, like if you are designing your machine. And also probably if your stator is working in this way, in a certain sense, this profile is kind of working in off-design condition, because it was very likely designed to have the stagnation point somewhere here. So yeah, it's worth fixing it, because it affects for sure the efficiency.
Yeah.
Well, I wouldn't run an optimization just to fix this, to be honest. Maybe the easiest is just maybe to have an exploration. Or what you could do, rather than already going for an optimization, is maybe running an adjoint calculation and having a look at the gradient or the surface sensitivity that is predicted by the adjoint, so that you can spot immediately which are the regions of the blade which are affecting the most your entropy generation, for instance. And in this way, you already know which are the areas in which you can you can have an effect. Yeah, and then of course, if you're still in design phase and not really into an optimization, what you can do is to play around with your design variables to have an effect on that region of the blade. So it could be, as an example, that you have a very high sensitivity predicted here because of this incidence. Not saying that it's necessarily the case, but it could. So what you could do is just playing with your design variables, such as the metal angle, maybe, to change the shape in this region. So I see another question. Yeah. Okay, thanks for that. Shall we go to lunch? Okay, so thank you very much for the attention, and see you at lunch.